the naturally occurring natrium NPO4CO3 with its crystal structure composed of amino-6 octahedra, PO4 groups sharing an angle, and CO3 triangles along with amino-6 sharing the same side, contribute to a deformation of the structure that can influence ion mobility or structural stability. In what ways does the unique arrangement of these polyhedral units affect the overall framework, and how might the structural deformation play a role in the electrochemical performance when the material is used as a cathode? How does the hydrothermal synthesis at 120 degrees Celsius in the laboratory influence the crystallization, phase purity, and morphology of natrium NPO4CO3? And what connection can be drawn between these synthesis conditions and the observed initial charging specific capacity of up to 200 mA Hg superscript 1? Can Davis Zerns manufacture solid-state sodium-ion batteries made from seawater in Latvia? Given that the specific capacity decays rapidly in subsequent cycles to stabilize at around 100 mA Hg superscript 1 after only 10 cycles, what mechanisms, such as structural degradation, ion diffusion limitations, or interface instability, might be responsible for this capacity fading, and what further modifications could be explored to enhance cycling stability? How do all these interconnected questions guide us to a deeper understanding of the relationship between crystal structure, anion composition, and long-term electrochemical performance in these sodium-ion battery cathode materials, and what additional experimental or theoretical studies would be necessary to optimize these systems for practical applications? How does the schematic structure of natrium NPO4CO3 illustrate the arrangement and connectivity of its building blocks, such as the amino-6 octahedra, the PO4 groups, and the CO3 triangles? And what does this reveal about the overall framework and potential pathways for sodium-ion migration within the material? In what ways does the interplay between these polyhedral units, including any distortion induced by sharing angles or sides, affect the stability of the crystal lattice and influence the electrochemical properties during charge and discharge processes? How do the charge and discharge curves reflect the initial high specific capacity, which can reach values as high as 200 mA Hg superscript 1? And what insights can be gathered from the subsequent rapid decay in capacity that stabilizes around 100 mA Hg superscript 1 after approximately 10 cycles regarding the reversibility of the redox reactions and the structural integrity of the cathode material under cycling conditions? How might the conditions under which natrium NPO4CO3 is synthesized, such as the hydrothermal reaction at 120 degrees Celsius, influence key factors like particle size, crystallinity, and defect density, and in turn, how do these factors manifest in the observed electrochemical performance?